This is Module 17 of Engineering Vibrations 1, an Introduction to Single Degree of Freedom Systems. Today's learning outcome is to actually do an example. We're going to solve for the transient response solution of a simple single degree of freedom system that is undamped and experiencing free vibration. And so the system we're going to look at is this laboratory equipment that I've shown you before, with the spring at the top, a mass in the center, and a damper at the bottom. And so this is my model with springs and dampers. I'm going to assume that all of the mass is in the center. I'm going to consider the spring and the damper negligible to the overall mass. And I've chosen my generalized coordinate as Q. And so all I'm going to do is I'm going to take away the damping. I'm going to say, hey, the damping is so small that we can ignore it, and I come up with an undamped system as shown here. Now I have another example of a system that is also a simple oscillator like this, and I want to show you that now. Here's another actual real-world system. This is an air track. I have a cart at the center, which is going to be my mass. It's connected on both sides with a spring and attached to supports on either end. It's riding on a cushion of air, so it's almost frictionless. So there's really very little damping in this case. And so as the system oscillates back and forth, this again is a simple single degree of freedom oscillator. So you can see the natural frequency in radians per second, or cycles per second. And you can also visualize now the period of oscillation. So we go one cycle. The time that takes to complete the cycle is the period of oscillation. And so another example of a simple single degree of freedom oscillator. So let's go ahead and model that air track. And we'll have our mass in the center. And we're going to have it attached at both sides with a support. And here are my springs as it oscillated back and forth. We could say that it was it's rolling on a cushion of air, and so we can just use that as frictionless wheels here. So it just moves back and forth, left and right on that cushion of air, frictionless. Let's say that the springs, the spring constant on this spring is K over 2, and on this spring is K over 2. Those springs are in parallel, and so I end up with the same sort of simple oscillator. I have a mass, okay, and I have my support. Now I'm just going to use one support over here. And since the springs are in parallel, this should have been K over 2. Since they're in parallel, now the spring is total K. And so these two systems are completely analogous. The natural frequency of that type of system is shown here. The period of oscillation is shown here. And we've done those before. And so here is our problem that we're going to solve. We have an undamped single degree of freedom system. It has a natural frequency of 79 hertz, or cycles per second. For the lab equipment, that would be very fast, but you can understand another system could have that high of a frequency. At time t equals 0, we're going to give it initial conditions of an initial displacement of 0.02 meters, an initial velocity of minus 49 meters per second. And we're to determine the max positive value of Q, the displacement that this vibration produces, and the time at which that first instance of the max value occurs. And so how do we start? Okay, what you should have said to yourself is, oh, let's look at the phase angle solution again. And I gave this earlier, the phase angle solution with the amplitude of displacement and the phase angle. This is just a simple harmonic oscillator. This was a graph of that oscillation. And so there's the phase angle form, and there's the phase angle itself. In this case, for the natural frequency, it was given in hertz, and so I want to go ahead and write that in radians per second in our equation. So I've got omega natural equals the 79 hertz, which is cycles per second. I'm going to multiply that by 2 pi radians per cycle, or per cycle. And that gives me a natural frequency of 496.4 radians per second. And for the phase angle, we'll put our numbers in again. And so I've got phi equals the tangent inverse of the quantity q dot 0, which was given as minus 49 meters per second, divided by omega natural, which we just found out to be 496.4 radians per second, times q dot 0. Q0, the initial displacement, which was 0.02 meters. And so the meters cancel out, the seconds cancel out. Seconds is in the denominator both times. And so we end up with our phi as equal to minus 1.37 radians. Okay, we'll continue on now. There's our response solution. I've put the numbers in. The only thing we're missing now is the amplitude of displacement, and that's capital X. And we have defined capital X and found it to be the square root of the initial displacement squared plus the initial velocity divided by the natural frequency squared, and the square root of all that. Okay, so let's go ahead and calculate that. We have capital X then equals the square root of q sub 0 squared, so that's 0.02 squared, plus the quantity q dot 0, which is minus 49, and I'm leaving the units off this time. The units come out to be meters, but we divide that by the omega natural, which was 496.4 radians per second. Let's go ahead and put the units in, actually. So we've got meters per second for the velocity, radians per second for the natural frequency. This would be meters. And so you can see the seconds cancel out over here. And the meters squared becomes, when you take the square root of that, it's going to be meters. And radians is dimensionless. And so we end up with the amplitude of displacement is equal to 0.101 meters. And so that's the maximum positive value of Q that this vibration produces. Because the max value of the cosine argument would be 1, and 1 times the amplitude of displacement would be the maximum positive value of Q. Okay, so now I've put in the amplitude of displacement, the natural frequency, and the phase angle. There is a plot And you can see that time 0 is here in the center. I've marked it with the red vertical line. There's my maximum amplitude of displacement, which is 0.101 meters. Here's the phase angle. Remember, to find the phase shift, I should say, it's set omega natural times time equals, omega natural t minus phi equals 0, and you come up with that time. And that's an example of phase lead, because the output, the first instant of the first peak of the output occurs before time equals 0. All right, and so we want to find, but that occurs before time equals 0. We want to find the first maximum value of Q, which is going to occur over here. And you can see that the cosine curve goes through 0 to 2 pi. And so the argument of cosine is 2 pi, where the first positive value of Q occurs. And so we have omega natural times time minus phi equals 2 pi to find out what that time is. And so we found omega natural to be 496.4. Phi was equal to minus 1.37. And so you can solve for time now. The time to the first peak equals 2 pi. A minus is a plus for the 1.37 term on the left-hand side, so that becomes a minus on the right-hand side, divided by omega natural, which was 496.4, and we find the time to the first peak equals 0.00990 seconds. And so that's the other part of the solution that we were looking for. So that's our answer. And so if I show that on my plot over here, you can see that time to the first peak, 0.990, and you can see where that lines up right about where it should be on the graph. And so that's a great example problem of an undamped single degree of freedom oscillator. And so we've solved for that example as a summary, and we looked at it and found the maximum amplitude and the time to the first peak, and we're able to analyze undamped and motion experience free vibrations. And I'll see you next time.